Session 3 and 4 taught by Dr. Reams in Black in 1977. This is Tape 7 Side B.
Now, what was your question?
You mentioned that it changes the elements.
Yes.
And we know that the atoms is their charge.
Sure, they lose anions and cations, but like your 12, your carbon 12.
So the 12 with the proton, the number of
It doesn't lose electrons, honey. It loses anions and cations from your cationic structure and anionic structure. But it doesn't, for instance, if carbon 12, it lost 11 of them, you'd have hydrogen 1.
from the
electrons. Well, protons are your cations, honey. Protons and cations is the same thing. Okay? Yes? They've given it a new name now, and I saw it last week. But it was a very common term 50 years ago, so probably you're going to have to get some older books. They call it now GAME, G-A-M-M-E, GAME. It's what we used to call Millhouse units. There's a new name for it, GAME, G-A-M-M-E. No, GAME, not gamma ray. GAME is a new word. It's been on. I only ran across it this last week, but I will verify that for you by tomorrow morning to see if I'm correct. G-A-M-M-E, GAME.
Mary.
G-A-M-M-E, GAME is what they call a Millhouse unit, a millionth of a millionth of a millionth of a part of energy. But 50 years ago it was called Millhouse unit. Now they call it GAME for some reason. What's that? I'd have to look it up on the atomic chart. This is why we need the atomic chart. What is the goal is 234, is that correct? On memory, I don't use it in ordinary food, so it's way up there, okay? No, not 234. That's uranium. There's two kinds of uranium, 234 and 237. Actually, it's two different elements, but they call them both uranium. And then there's plutonium, which is in that same category, which is also, and then there's radium, which is also in that same category. Now, radium, Madame Curie made radium, and then they left 1 gram of it to go have lunch, and when they come back, it was gone. In other words, it evaporated into the air. It had given up all of its cations and was no longer in existence anymore. Then they had to work through another, 17 tons of iron to get another gram out. Now, when you have enough of the radium and iron, then it's magnetized. It's a magnet. In other words, it's the difference in radiation in the iron. It's the difference between a magnet and a non-magnet. So, what makes a postage stamp stick to an envelope? It's the ionization of it, yes. The ionization. In other words, the attraction. It's both cationic, and yet it sticks. If one was anionic and one was cationic, what would happen? What's that? It would burn, yes. Combustion. It would start combustion then, burn the paper. Isn't this easy? Isn't this easy? It's baby ray stuff, yes.
You said a change in cations brings charge, and a change in the electron brings a change in cations.
Well, a change in cations would be a change in, no, it could be. I mean, a change in cations would be a change in element, yes. But a loss of cations or anions could mean a different product, or in other words, a different hardness or different kind of. For instance, hydrogen. Let's take, I wish to screw this thing down the way it would stay put. For instance, let's take hydrogen. Let's suppose that hydrogen is a 1 and a 1, or vice versa. It can be either way. It can be, in other words, this is two different atoms here, okay? This one should have, that's right. Now, it's an isotope, so you can have the plus in the middle or the plus on the outside, the cation on the outside, or anion. Now, let's take hydrogen in its simplest form would be 1 plus 500. Let's take it in its most complicated form. Hydrogen would be 499 plus 999 in its most complicated form. It's still hydrogen. What's that? Yes, that makes a difference in density, yes. An increase in anions and cations means an increase in density, yes. Now, which would weigh the most? Hydrogen 1 plus 500, the atom, or hydrogen 499 plus 999? No, they would not weigh the same. Which one would be the largest? They'd both be the same size. They'd weigh the most, yes, but they'd both be the same size under the same temperature and pressure. If that were not true, there wouldn't be any such thing as weight. A table of weights. Are you beginning to comprehend what this is about? No. Well, yes, your number one up there, yes, is. In other words, the one indicates it's somewhere between it's between these two here. The atomic weight there means that there's one cation out there. It doesn't mean there's a variable there, but it means there's one cation out there is what it means. So the greater number of cations, the greater the weight of the product, yes.
Are you saying that all inside?
Yes, under the same temperature and pressure.
Even though one may have one shell around it and they have the 10 shell, whatever.
Right, yes.
So the shells do not.
That's right. And the lighter ones. Right.
Very hard.
For instance, that's not very hard to understand. Suppose you had a quart cup, and you had some real small beads, so small that you had to have a magnifying glass to put them in there. And then you had some as big as ordinary marbles that you play with. Which one could you put the most in, the small ones or the large ones, in the same size container? The small ones. It's the same principle. When you put, let's say, 100,000 small ones in that container, was the container any larger than you put the 150 big ones in? Was the container any larger? Still the same size, wasn't it?
Are the larger elements that have electrons, that the shells of those electrons were elements?
The nuclei.
So that the peripheral dimension is the
Honey, it isn't quite like that. It's not quite like that. Would you say that it's like saying there's the skin of the orange, of a big orange, closer to the core than the small of than the skin of a small orange? Is it closer to the core? It's the same distance. In ratio, if you did, it wouldn't be an orange, honey. What's that?
The diameter.
I'm not talking about diameter.
But the closeness is supposed to be.
The ratio. You're working with ratios, dear. It would be the same, or else it wouldn't be an orange. The ratio. We're talking about anion and cationic structure. The ratio is the same. Do you follow me? The ratio is the same. If you didn't, it wouldn't be an orange, because you'd have a change in your cationic and anionic structure. You'd have some other fruit. Now, this does make a difference in variety. The cationic and the anionic structure of citrus gives you a different variety. There's over 200 different varieties of oranges grown in Florida. And there's over 50 different varieties of grapefruit, and there's over, over 100 different varieties of tangerines grown in Florida. Now, some of the ones, it's very difficult to tell the difference between a tangerine and an orange. So, I mean, you could flip a coin as to tell whether it's an orange or a tangerine. But it's only the way out that we can distinguish. Now, what I'm trying to get across to you is the picture of things that we've got to comprehend in order to imagine things small enough to be energy. Now I'm going to draw you a picture here. Yes? Yes. 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 He said, am I referring to the ratio between the elements, and am I referring to the shell around it. For instance, I think there's some confusion here. I'm going to try to straighten you out on to help you understand some things that's confusing you. For instance, let's draw some compound structures here. Now there would be, we will say, somewhat of the placement of the atoms in a drop of water. About 5 million of them. About 5 million of them in one drop. Now, if you shot an electrical beam straight through the water, it would not go through the atom. It would go in this, it could go in this direction, you see. Moving in straight lines, you see. Oh, I'm sorry. Thank you for helping me. Now, you see, it would move in straight lines. It would not go through the atoms. Do you follow me? For instance, a submarine on the bottom of the ocean can talk to a radio station up on the land. So there is enough space between the atoms in the water for an anionic beam to pass, and it doesn't go through the atom, it goes between the atoms of water. Is that clear? For instance, the radio in the room can send a beam right straight into the room, right through the wall, or right through the cities, or right through the clouds, and everywhere, and then take that anion into your tubes of your radio, or the various parts of the radio, and out will come music or voice and so forth. Now, those beams travel in a straight line. Now, I imagine that beam is so strong that if it strikes an atom, the atom would bounce off. But the beam would still go ahead and clear. Suppose that one got channeled in the wrong way. There's another one right behind it that it knocked, say, this one out of the way, and the next one behind it then would have the straight line to pass on through. Are you following me? Now, at what speed do they travel?
Travel at light.
That's right, miles per second. Okay. That's the speed they travel. 186,000 miles, 186,400 miles per second. Now, providing what? There's one provision. Less resistance. Less resistance, yes.
Steel will kill a radio pack.
Right. Less resistance, that's right. So will lead. Now, let's go ahead and study this a little bit more. You say, well, what has this got to do with our body? It's got everything in the world to do with our body. We'll show you in just a few minutes. For instance, the Earth's surface, this is the Earth's surface, and 100 miles up here, 100 miles up, this is up this way, is the Van Allen belt. Now, the Van Allen belt is negative. It's anionic. The Earth is cationic. The anions are all trying to get back into Van Allen belt, and the cations are all trying to get back into the Earth, as you will learn in Course 5. Now, the lightning that passes through the atmosphere, down about 1 mile to 2 miles high, the scale is not very accurate that I'm drawing out here. Whenever the cationic forces go up to the top of a tree, and the anionic forces from the lightning are lost here due to atmospheric conditions, then we say lightning strikes. There's a short circuit. In other words, cations have met anions, and that is what lightning is. And what? Terrific amounts of energy is given off, lost between the two kinds of electricity. Now, let's go above the Van Allen belt now and see what happens. Well, it's a useful function if you want to get into it, but there's a loss of energy between the two poles, what I'm getting at. Now we're talking about above the Van Allen belt. Now we'll say the sun is out here 93 million miles away, the sun. 93 million miles away. So, now then, between this Van Allen belt, above that there's no atmospheric pressure. So no one knows out here what the speed of light is. No one knows what it is out there. I mean, it's much greater than it is between the Van Allen belt and the Earth. Now, the scientists have said under the same pressure of the Earth, between the Earth and the Van Allen belt, the sunlight could go out and it would be 8 years before we missed the sun being out. But the thing about it is, there is no resistance out here, so it's instantaneous. So because there's no resistance, then there's darkness out here. It's very dark. It's very dark out here because there's no resistance. In other words, these anions only give off light when there is resistance. And light doesn't start till you get to the Van Allen belt. And then it's very dim as you get near it. Now, are you beginning to understand what energy is? What I'm trying to explain to you is what energy is. Do you begin to comprehend something about energy? If the resistance between the Earth and the Van Allen belt was equal all the way to the sun, we're told by astrology that it would take 8 years before we'd miss the sun being out. Now, your vision is a little different because your vision is not restricted by normal atmospheric pressure unless there is a shadow. Unless there's a shadow, it's not restricted. For instance, you can look up into the night and look hundreds of millions of miles away and see the stars, the constellations, on a clear night. But if there's fog out there, you can't see them. If there's too much light, you can't see them. In other words, we're living in a spectrum, the same as using a microscope. Turning it, and you get too much light, you don't see anything. You've got to dim your light in order to bring, if there's anything under the scope in focus, then you can see it. But too much light vanishes it away. Yes? Only as the light years is only true as far as the atmospheric pressure of the Earth is concerned. That's right. Yes. I do not know. I do not know. The radiation would change, but I don't know whether it would be enough for us to measure or not. Now, let's get on to how this applies to you and me. What I was trying to do was to explain to you about energy. When you smell a rose, what is it you're smelling? Energy. That's right. It's a piece of that rose. When does the rose smell the sweetest? When it first opens or just before it fades? I see you do. When does the rose give off the most energy? As it's fading or as it's opening? That's right, sir. The fragrance is greater as it fades. Right. As it's fading, yes, the greater amount of energy it gives off, the greater fragrance. Well, that depends on what stage that it's in. That's right. Well, there's a difference in idea. Some people don't like the odor of polecats, but others love it very much. That's a matter of taste and a matter of smell. Some people walk into a laboratory and they smell hydrogen sulfide. They turn up the nose. That stinks. Well, to the chemist, he doesn't pay any attention to it. He smelled it so many thousands of times, it doesn't make any difference. He just soon smell hydrogen sulfide, which you would say rotten eggs, or as any other odor that practically comes out of the laboratory, provided it didn't cut off the supply of oxygen. Then you notice it very much. But smells, some people prefer violet over rose, and some prefer orange blossoms, and some prefer Old Spice, Old Leather. So that's a matter of preference. So what I'm talking about is how much energy is given off. Now, when you have a banana and it gets black spots on it, those black spots are banana cancers. Yeah. Sure. Sure. What is cancer? It's a decaying cell. That's all it is. A decaying cell. In other words, it's cationic phenomena going back to dust. Thus we are, to dust we shall return. And whenever it loses its power of ionization and cannot give off any more energy, then it's cancer. Whether it's in a human being, whether it's in a banana, or a tomato, or a pepper, or an eggplant, it's cancer, period, as far as it's concerned. So, did you ever eat cancers? Sure. All of us have.
Doctor,
yes?
which is the better for you than one black spot?
I'd have to see your numbers to know. So, what I was trying to get across to you, cancer is not that great big bugaboo that the drug syndicate would have you believe. Cancer is premature aging. Or, in a banana, it's a normal process. Whenever it's ripe, then it begins to, what determines when a banana is ripe, or an orange is ripe, or an apple is ripe, or a watermelon is ripe? What determines that? No. No, there's something there that determines when it's ripe. Now, what is it? When the seed is complete, mature. When the seed is mature, then it starts to die. Now, what's that? When a seed matures, then it starts to die. Now, you take a bean bush, or peas, or something. If you'll keep all of the beans picked off, or the peas picked off, before they reach maturity, then the plant will keep bearing and bearing and bearing, trying to leave offspring. But if you let them mature, then the plant dies. So, what I'm trying to tell you is that cancer is only premature aging. Now, what is premature aging? Well, Methuselah lived 969 years before he died of cancer. Loss of energy, that's all cancer is. It's no big bugaboo at all. It's something that the devil tries to scare hell out of you with. That's all it is. And it's a mineral deficiency. So what we're trying to do is to simplify things and express it in plain English where you can understand it. Now, for instance, let's take an equation that we've had, and we'll say that the number was 3.5. I need a pencil that writes clear. Yes? Well, there's a miracle. God took him. And like Methuselah, he says, and he walked with God and was not. There are times when there's a loss of energy, but God took Moses, and Moses is not in the grave. The devil disputed over the body of Moses, so God took him to heaven, and he was seen there at the greatest prayer meeting that was ever held on earth, when there was only 4 people there, Peter, James, and John, and the Messiah. The greatest prayer, he was seen there. So there was Elijah, who was taken up in a fiery chariot. Remember the lecture I gave you on the ionization of our celestial bodies? If you don't have it or haven't heard it, you ought to get the tape on it. Of what our bodies were like in the Garden of Eden and what they'll be like after we are translated, after there is no time. In Revelation there'll be no time anymore. Now, let's get back to our subject here. Let's take an equation here, 3, and we'll take 660 over, we'll take it over 6. We'll take a 23C, 4M, and a 6 over 8 equation. What does this equation note? What's the first thing you think of when you see this equation? The first thing I think of is what is perfect. this is what I think of. When I first see the equation, the very first thought that comes in mind, how far from perfect is it? How far from perfect is it? Now, really, how far from perfect is it? Just plain simple arithmetic here. The equation that I gave you was 660 over 600, 23C, and 4M, and 6 over 8. And the next one I gave you was perfect, the one written above it. And then we subtracted it, and we came up with 1.5 minus 20 plus 40, 17C? 16C, and 4M was not enough difference to change the difference in that one. And then 3 over 5. So this is what we see now. Now, this is a loss of energy. Now, suppose that you made a diet. You made a diet now. The first thing you would realize that you were dealing with a person that had low blood sugar. You'd also see by this equation that the person was not drinking enough water, or the water was contaminated that they were drinking. You would see also that their eating habits did not fit their body chemistry. You would also see that the body was retaining too much salt, and the first thing they'll tell you, well, doctor, I haven't used salt in years and years and years. I haven't used any salt. It isn't how much you use that counts, it's how much your body retains. For instance, all the vegetables and all the foods and all the fruits have vegetable salts in them. Now, there's two kinds of salts. Who will tell me what kinds, the two kinds of salts there are? Well, yes, but there's, I was speaking chemically speaking, there's two kinds of salts. What kind are they? There's the chloride salts and the non-chloride salts. And there's a great group of the non-chloride salts. Can you name one that's a non-chloride salt? Potassium is a salt, yes. Can you name some more? Proteins are salt. They're nitrogen. Nitrogens are salts. Insulin is a compound salt. So you see, what actually do salts do to our bodies? What do they do? They're an electrolyte. That's right. The salts are an electrolyte. What happens if the salt drops too low for too long a period? That's right. The brain doesn't carry the electrical waves from the brain to the various organs. If it stays too long, a day or so doesn't make a lot of difference, but continuously it would. You're going to find people at times that the salt and the urine drops to zero, but that doesn't mean that it's zero in their whole system. It just means that the body has got to the point that it can't throw off anymore, because if there was not any in the whole system, they'd be seriously dead, because there'd be no communication between the brain and the body. See, what I'm trying to tell you is to use common horse sense with these things and put them together and they form a picture. Try to logically reason them through. God put a nut on every one of your shoulder, between your shoulders. It's called the head, and it's sometimes a part of the body that's used the least, especially the brain. Now, what I'm trying to teach you here is to think these things through instead of memorizing things through. There's a certain amount of memory you've got to do. You've got to memorize the laws of physics. There's no way to learn these things, to logically reason them out without the laws of physics. You've got to have those laws. You've got to obey those laws. You must obey those laws in order to comprehend and to understand what these numbers are saying. Now, the first thing that you would see when you have this number is that well, I would reason that the person does not need to be into a retreat. Why? Because the numbers are within the bounds that they don't need to be into a retreat, that they can do this at home. Now, I'm speaking about first test now, first test. So I would put this person on lemonade and water according to the age, height, and weight that you were given in course 1. And also, I would add a sweetener to the lemonade each day in order to keep the energy from dropping too low. You can expect this person to go through a mild withdrawal because the body chemistry will change. It would be a very good idea if they could stop working for the first week with this kind of a diet, especially if they're over 40 years old or even 35, and do nothing but this, just this. If this person was a person that was inside quite a lot, the 4th, 5th, and 6th day, I would suggest that they start walking a little and more each day. But you may find a person that walks a terrific lot with the same numbers, and therefore, if you do find a person that does strenuous work with their hands, arms, legs, and feet, then they must stop for a week. And under that condition, it's best, unless they will really cooperate with you, that they be to a retreat, because a lot of them thinks it won't hurt to do this, it won't hurt to do that. I'm home this week, I'll mow the yard, I'll make the garden, I'll wax the car, I'll do these 10,000 odd jobs that my wife has been wanting done now for the last 6 months, and the diet won't take. Now, when you say do nothing, you mean absolutely do nothing. Because if you burn up each day the amount of energy that you're supposed to gain, then these numbers are not going to be effective or even change very much. A person with this kind of numbers should have a test about once per month. This is putting meaning into numbers and reasoning it through. Are there any questions about this thinking now? What I'm trying to do is to get your minds in gear, to logically think these things through. Now, after the 6 days, what minerals would you say that this person needed? Well, I would say that they needed vitamin D, because the liver bile is too acid. That is after the fast, providing the numbers, probably the fast wouldn't change. The pH of 6, it wouldn't change it. It probably would change the top number, drop it a little. In other words, these two would try to stick the level while they were on the lemonade fast. Yes, 3 days. Now, no, I said the lemonade and water would drop it. Also, now if the person was overweight, I mean way overweight, too much fat, I'm not talking about muscle, then it could be a 6-day fast, 3-day light diet, and another 6-day fast, but they would need to be off work for 21 days in order to get their body chemistry back into a level. Because actually, if you have a person that's not much overweight, that we'll say that weighed 340 pounds, or a woman that weighed 290 pounds and was only 5 feet and 4 inches tall, I would suggest that you send those to a retreat. And I'll tell you why. Because some days the fat turns to sugar a lot faster than others. Their own fat will turn to sugar. And other days it doesn't. And some days they will need carbohydrates in their lemonade, and some days they won't. Now, in a very few months, we're coming out with instruments that you will sell that the people can take home and test their own, and a lot more people won't have to be in a retreat because they can do this themselves at home. But at the present moment, those instruments are not available, but they will be available very soon. And they're not made like your refractometers. They're made so that the average family can use them. And then if it's in the red, they see their tester or their doctor. But if they're between the reds, then it tells you what to do. And this way, they can help you and help themselves. And still, they need to come back in a month, even if they have that instrument, because the pH may rise above 640, or may go on up to 7. It generally overdoes itself. It over-exaggerates. You'll need to take them off of Cal-2. You'll need to take them off of vitamin D. And in this case, they can take the 400 milligram vitamin D instead of the 10,000 units vitamin D. But suppose now they come back in a month, and you find a reading something like this. In a month they come back and you find a reading that says 0.6, and it says, where we say 7 over 6 still, and it still says 20 C, and the 4M, and it has, we'll say, 1 over 7.
Dr. Reams, I've got to change the tape. Is the tape